Welcome to this comprehensive mathematics lecture on probability, designed specifically for Class 10 students. Probability is the fascinating branch of mathematics that quantifies uncertainty, measuring the likelihood of events happening in our everyday lives. From predicting weather patterns and modeling stock market risks to assessing medical diagnostics and game theory strategies, probability is the key tool used to make decisions under uncertainty. Historically, the formal study of probability began in 17th century Europe, arising from correspondences between mathematicians Blaise Pascal and Pierre de Fermat regarding games of chance. Today, we will master the classical definition of probability, explore events that are certain or impossible, and solve real-world problems involving coins, dice, and playing cards step by step. Let us dive in. To calculate probability mathematically, we first define an experiment, which is any process that leads to well-defined outcomes. The set of all possible outcomes of an experiment is called the sample space, denoted by the capital letter S. An event, denoted as E, is a subset of this sample space. The classical definition of probability, established by Pierre-Simon Laplace, applies to experiments where all outcomes are equally likely. The probability of an event E, denoted as P of E, is defined as the number of outcomes favorable to E, divided by the total number of possible outcomes in the sample space. This ratio always lies between 0 and 1, inclusive, representing a scaling from impossible to absolutely certain. Every probability value represents a ratio that is strictly bounded between 0 and 1. An event that has 0 chance of occurring is called an impossible event, and its probability is exactly 0. For example, rolling a 7 on a standard 6-sided die is impossible. Conversely, an event that is absolutely guaranteed to happen is called a sure or certain event, and its probability is exactly 1. For example, drawing a marble that is either red or blue from a bag containing only red and blue marbles is certain. Furthermore, for any event E, we define its complementary event, E bar, which represents E not occurring. The sum of the probability of E and its complement E bar is always equal to 1, meaning P of E plus P of E bar equals 1. Let us examine one of the simplest probability experiments, tossing a fair coin. When we toss a single coin, there are two equally likely outcomes, heads or tails. The sample space is H and T with a size of 2. The probability of getting a head is 1 over 2, or 50%. If we toss two coins simultaneously, the sample space expands. The possible outcomes are both heads, first head second tail, first tail second head, and both tails. This gives a total of 4 outcomes in our sample space. If we want to find the probability of getting at least one head, we look at the favorable outcomes, HH, HT, and TH, which is 3 outcomes. The probability is therefore 3 over 4, or 75%. Now let us consider rolling a standard 6-sided die. The faces of the die are numbered from 1 to 6, so the sample space S contains the numbers 1, 2, 3, 4, 5, and 6. The total number of outcomes is 6. Since the die is fair, each face has an equal probability of 1 over 6 of landing face up. Let us solve some simple problems. If we want to find the probability of rolling an even number, our favorable outcomes are 2, 4, and 6, which is 3 outcomes. The probability is 3 over 6, simplifying to 1 over 2. If we want to find the probability of rolling a prime number, our favorable outcomes are 2, 3, and 5, which also gives 3 outcomes and a probability of 1 over 2. A standard deck of playing cards contains 52 cards, which are divided into 4 suits: spades, clubs, hearts, and diamonds. Spades and clubs are black suits, while hearts and diamonds are red suits. Each suit consists of 13 cards, ace, numbers 2 through 10, and 3 face cards called the jack, queen, and king. The total number of face cards in a deck is 12, consisting of 6 red face cards and 6 black face cards. Playing card problems are a classic mathematical exercise. Because the deck is well shuffled, drawing any single card is an equally likely experiment with a total of 52 possible outcomes, allowing us to compute precise ratios for any card combination. Let us solve two standard card problems using our classical probability definition. First, suppose we draw a card at random and want to find the probability that it is a red face card. Favorable red face cards are the Jack, Queen, and King of Hearts, and the Jack, Queen, and King of Diamonds, which totals 6 cards. The probability is 6 over 52, which simplifies to 3 over 26. Second, suppose we want to find the probability of drawing an ace. There are 4 aces in the deck, 1 for each suit. The probability is 4 over 52, which simplifies to 1 over 13. By counting the favorable outcomes exactly, we resolve card probabilities easily. Probability is frequently applied to analyze selections from mixtures of objects. Suppose a bag contains 5 red marbles, 8 white marbles, and 4 green marbles. If one marble is drawn at random from the bag, what is the probability that it is not green? First, we calculate the total number of marbles, which represents our sample space size. Summing 5, 8, and 4 gives 17 total outcomes. Next, we find the number of outcomes that are not green. These are the red and white marbles, which sum to 13 favorable outcomes. Using our formula, the probability of drawing a non-green marble is 13 over 17. This simple ratio represents the likelihood of this everyday physical event. Another common application of probability is in quality control and manufacturing. Suppose 12 defective pens are accidentally mixed with 132 good ones. It is not possible to tell them apart just by looking. If one pen is taken out at random, what is the probability that the pen taken out is a good one? First, we find the size of the sample space by adding 12 defective pens and 132 good pens, which equals 144 total pens. The number of favorable outcomes for getting a good pen is 132. The probability is 132 over 144. Dividing both numbers by 12 simplifies the fraction to 11 over 12. As we conclude our study, it is important to distinguish between theoretical and experimental probability. The classical probability we calculated today is theoretical probability, which is based on equally likely mathematical outcomes without performing trials. In contrast, experimental probability is based on actual observations and physical trials. If you toss a coin 10 times, you might get 7 heads and 3 tails, giving an experimental probability of 70% for heads. However, as the number of trials increases to thousands or millions, the experimental probability converges closer and closer to the theoretical probability of 50%. This fundamental concept is known as the law of large numbers, which bridges mathematical theory and real-world experiments. Let us summarize the core principles of Class 10 probability we have learned today. First, probability measures likelihood on a strict scale from 0 to 1. Second, the classical formula requires dividing the number of favorable outcomes by the total outcomes in the sample space. Third, the probability of an event and its complement always sum to 1. Fourth, we can solve problems involving coins, dice, playing cards, and mixed items by carefully listing the sample space and favorable sets. By mastering these principles, you possess a powerful analytical framework to model uncertainty and make logical decisions in mathematics and daily life. Thank you for attending this Class 10 Mathematics lecture on probability. We hope you have built a clear, intuitive understanding of sample spaces, event likelihoods, and card, coin, and die calculation techniques. If this video helped you visualize math and uncertainty, please subscribe to our learning channel, hit the like button, and share it with your classmates. Don't forget to click the notification bell so you never miss an academic update. Keep practicing, keep calculating, and we will see you in the next mathematics lecture.